Good afternoon, friends. Welcome to mathematics lecture of Bisect lecture series. Today we are going to have one very interesting lecture on applications of matrices. In our studio, we have Professor V.R. Trivedi, who is going to speak about this applications of matrices. We are going to discuss mainly three applications. One is you can see on your screen. You can see on the screen that we are going to study the following three applications. One is solution of system of linear equations. Secondly, transformation of geometrical objects, and computation of determinant. So I request Professor V.R. Trivedi to talk about these three applications of matrices. I hope you will enjoy this talk.
Welcome to the world of applications of matrices. You can see on the screen, given a system of n simultaneous linear equations,
Screen पर बताओ सब.
on the screen you see the system of simultaneous linear equations. There are m equations in n variables, and in short you can write this as aij xj, j varies from 1 to n, b I varies from 1 to n. So what you see on the screen, they can be written in short this way. Now, expressing columns as C1, C2, Cn, then the system of equations 1 can be expressed as x1 C1 plus x2 C2 and so on, xn cn equal to b, where c1 c2 cn are n columns of the matrix A, which is called the coefficient matrix of the given system of equations, where ith column ci, you just see on the screen, is
A1 J.
A11, A21, so on, AM1 and so on. Last column Cn is A1n, A2n, so on, AMN, and constant column is B, that is B1, B2, Bn. Here B depends on column C1, C2, Cn. Therefore, number of linearly independent columns in the matrix A is same as number of columns in the matrix A, columns of A, and you attach the n plus 1 column as B. So, you have, whenever B depends on that, you have a solution. And that solution is possible if a total number of linearly independent columns in A is same as number of linearly independent columns in AB. That's called the augmented matrix of the given system of equations. So, number of linearly independent columns is denoted by RA, or column rank of A, that is maximum number of linearly independent columns in A, and that is same as number of linearly independent columns in AB. So, if number of linearly independent columns in A is same as number of linearly independent columns in the augmented matrix AB, that is rank of A equal to rank of AB, then the system of equations here B, that is the column of constant is not 0, then it is called NS system of equations, and if B equal to 0, then it is called S system of equations. So the NS system of equation has a solutions if rank of A equal to rank of A equal to rank of the augmented matrix A B. Now onwards we'll take number of rows m equal to number of columns. So in that case, that is number of equations equal to number of variables. So now onwards A will be a square matrix. So in that case, the H system, that is Ax equal to 0, the H system Ax equal to 0 has solution x equal to 0 as the only solution. That's called also trivial solution. Then this is true if and only if the columns of A are linearly independent. You just see on the screen, and that is if and only if rank of A equal to n, and that is possible if and only if the row reduced echelon form, in short RRE, matrix of A is the identity matrix IN, and that is true if and only if A is invertible, non-singular, and that is true if and only if determinant A is not 0. That you can see on the screen, and whenever the NS system AX equal to B, corresponding system is S system, and whenever S system has unique solution, then has unique solution, the only solution, then we have seen that determinant A is not 0 and rank of A equal to rank of AB equal to n. If that system has non-trivial solution also, that is x not equal to 0 is also a solution, then in that case it has infinitely many solutions, and you use contrapositive property, that is this is the contrapositive property, P implies Q equal to not Q implies not P. So we have seen that the S system of equation has a solution, unique solution, that is the trivial solution if and only if rank of A equal to n and A is non-singular. So if the system of equation has non-trivial solutions, that is infinitely many solutions, in that case A is singular and rank of A is less than n. So now we come to the NS system of equations. S system of equations, we have seen that it has always a solution, so system is always consistent. Either it has a unique solutions or infinitely many solutions. But when you come to NS system of equations, that is AX equal to B, there are three possibilities. One, it has no solution. In that case, B is not depending on columns of A, that is it is independent, then you don't have the solutions. If it has unique solutions, then of course rank of A equal to rank of the augmented matrix AB, and here rank Yes, you see on the screen. On the screen you have seen that system of equation Ax equal to b, where b is not equal to 0, has either no solutions or unique solutions. Unique solutions if and only if rank of A equal to rank of the augmented matrix, and that is equal to n, and that is true if and only if A is non-singular and row reduced echelon form of A is in. And determinant A is not 0, and unique solution is x equal to A inverse B. The unique solutions you get x equal to A inverse B. If again it has infinitely many solutions that you can see on the screen, if and only if rank of A is less than n. Now let's see. So once you have the general solution of the H system of equations, Ax equal to 0, that solutions we call the complementary functions or complementary integral of the NS system, and one particular solutions you have of the NS system Ax equal to b, then particular solutions plus Ci, that gives the general solution of the given NH system of equations. Now we have seen that NS system of equation has no solutions or unique solutions, that is x equal to A inverse b, or infinitely many solutions. Whenever it has infinitely solutions or unique solution, the system is called consistent, otherwise it is called inconsistent. So let us see some problem. The first problem you see on the screen, the NS system of equations, that is x plus 2y minus z equal to 0. Second equation is minus x plus 3y equal to minus 4, x plus y plus z equal to minus 1. In the matrix form, this can be written as just see 1 2 minus 1 1 2 minus 1, and from constants 0 we are not writing x y z. This is the augmented matrix of the given system of equation, that is NS system of equations. Second row is minus 1 3 0 minus 4, and third row is 1 1 and minus 1. So that is same as Ax equal to b. So now we take this augmented matrix A by B, where first column is of x, second column is of y, and third column is of z. Now we apply elementary row operations and reduce it to the row reduced echelon form. First we take the operations R2 plus R1 and R3 minus R1. When you take these operations, in second row you are adding first row, and in the third row you are subtracting first row. The resultant you see is 1 2 minus 1 0 0 5 minus 1 minus 4 0 minus 1 2 minus 1. Now we operate, we interchange second and third row. we interchange second and third row. The new matrix so got, then we operate in the new matrix, we add 5 times second row to the third row, that is called R3 plus 5 times R2. In that case we got 1 2 minus 1 0, first row as it is, second 0 1 minus 2 1, and 0 0 9 minus 9. We operate at the same time, we divide second row by minus 1. So we got the second row as 0 1 minus 2 1, and now we divide this matrix, third row, by 9. So we operate 1 upon 9 in the third row, that is 1 upon 9 R3. So in that case we get 1 2 minus 1 0 0 0 1 minus 2 1, and 0 0 1 minus 1. Now we operate two operations together. In the second row you are operating 2 times third row, and first row you are adding third row. In that case we get the resultant matrix 1 2 0 minus 1 0 1 0 minus 1 0 0 1 minus 1. Now we operate from first row, we are subtracting 2 times of second row. In that case we got 1 0 0 and 1, then 0 1 0 minus 1 0 0 1 minus 1. Now the given matrix of coefficient reduced to identity matrix, and first column is X column, second column Y column, third is Z column. So directly we got the solution: X equal to 1, Y equal to minus 1, and Z equal to minus 1. And we have seen that if the given matrix by elementary row operation is reduced to identity matrix, you have a unique solutions. And here